Hello friends, welcome to Experimental Physics, and this is after a long time that we are meeting. So today's video is going to be about sound, and specifically we'll be calculating speed of sound in air. For this we'll be making standing waves, and using those standing waves we can calculate the speed of sound. These standing waves are nothing but a condition of resonance in case of sound waves. Now, what is a resonance? In resonance, a systematic force is applied at a specific frequency. The frequency matches with the frequency of the object on which the force is getting applied. The amplitude of the oscillation of the object increases, and it goes on increases up to a certain limit, after which the amplitude cannot increase because of the losses. The losses also increase. Well, that amplitude is quite large, and that given situation is what we call a standing wave or a resonance. We can create this standing waves of sound in basically two ways. In one way, we can use a pipe which is open at both the ends. There is another way which we are going to use today. In that method, we'll be using a pipe which is open only at one end. I have a frequency generator app in this mobile and a bucket full of water, and I'm going to place the lower end of the pipe into the bucket such that water perfectly closes this end, and I'm going to place the mobile on the other end of the pipe, and I'm going to lower this pipe into the bucket. Because there is water and water remains at the horizontal level, as I dip the pipe more into water, the length of the air column decreases, and that length, because of that changing length, we can create a standing wave. Now, many of the students find it very difficult, and they cannot comprehend physically how a resonance of sound wave actually look like, or in this case, how does it change the hearing pattern. Is there any difference in the sound intensity? And today's experiment is going to about that. Okay, so we have made the setup. We have this water container here. I have connected the microphone at the top end of the tube, right? So first of all, let me start the sound so that you can hear it. Now this is 4 kilohertz frequency, remember. So now the mobile is exactly above the tube, and I'm going to bring it up. Listen when you will hear the high intensity sound, okay? This is the first resonance. See? Second. Third. Fourth. Fifth. And we are out of the tube, out of the water, right? So I have counted 5 points where there is resonance. Now I also have another angle. I did the same experiment, and I kept the video camera close to this setup so that you can see the readings, see the markings on the scale, and we can note that markings at which we are hearing the high intensity sound. We'll get those markings, and from that we'll get our lambda. So let's do that. So as we saw in the experiment, as I was changing the length of the air column of the pipe, there was a distinct change in the intensity of the sound, and the time instant at which we were hearing maximum sound, the highest intensity sound, is the point at which resonance is occurring. Now what do we mean by resonance? Well, I have drawn a diagram here that indicates some of the cases at which the resonance might happen. Now these structures here are called standing waves in an open organ pipe. Class 12 students very easily recognize this. Now why I am saying that this is an open organ pipe standing waves? Because at one end you can see that antinodes are forming, and the other end the nodes are forming. This happens only in an open organ pipe. Now why these three cases are important to us are because these three cases indicate the consecutive lengths of the tube for which a standing wave might be created in the pipe. The difference between these two lengths is lambda by 2. If we subtract this length from this length, we will get lambda by 2, and if we subtract this length from this, we again get lambda by 2. When I was changing the length of the pipe, when I was inserting it inside or when I was pulling it outside, the two time instances at which you heard loud intensity sound, the difference between the length of the two pipes at those instances was lambda by 2. In our experiment, we are assuming that speed of sound is not changing over the course of period, and also we are deliberately not changing the frequency of the source. We can guarantee that wavelength of the sound wave will not change. Now we know the average value of sound in air, and it is almost 340 meter per second. In some question it might be given to be 330 meter per second. Now this always puzzled me that why does the speed of sound changes according to the question, and the reason is that the speed of sound depends on the temperature, the density of the gas that you have, and there are a lot of factors. So we hope to get the result that we generally see in the books, which is 340 or 330 meter per second, but I'm not sure that what I'm going to get. So as you can see, I have written the readings here for the phi resonance. If you remember, I said the separation between the two consecutive lengths for resonance would be lambda by 2, right? So now if you look at here, the separation between these two is 4.5 centimeter. Again here it is 4.5, here it is 4.5, but here at the last we are only getting 4 centimeter. So there is definitely human error. So in order to minimize the human error, we are going to use method of averaging. If I subtract this length from this length, I get 17.5 centimeter. Now from this point to this point, every separation is of lambda by 2. This is lambda by 2, this is lambda by 2, and so on. The total separation from here to here must be 2 lambda, 4 times lambda by 2, right? So if we write it down, we get 17.5 as 2 lambda. From that we get lambda equal to 8.75 centimeter, which is in meters 0.00875. If we put it in our speed equation, which is frequency into wavelength, we get speed of sound to be 350 meter per second, which is actually a very good result, knowing that we might have made many errors in the experiment. The main purpose of this experiment was to make students physically understand what is the meaning of standing wave and resonance in case of sound wave and the whole organ pipe idea. So if you like our video, please subscribe to our channel. It encourages us to make more such videos. Thank you very much.